All right, so modulus, an argument of a complex number. So if you have a complex number z, which is x plus iy, if you have, sorry, the complex number z is x plus iy. So if you have z and you have two strokes beside it like this, you'd read that as the modulus of the complex number z. Now, the symbol for the modulus is r. So r, which is the modulus of the complex number z, is equal to the square root of x squared plus y squared. And if you're quick enough, you'll actually see that that is an application of Pythagoras theorem. So the modulus of the complex number is sort of like the length of the line OZ. So if this is the line OZ, the length of that line is the modulus of the complex number. So if this is a right angle triangle, this is x and this is y, Pythagoras theorem says that r squared would be equal to x squared plus y squared, where r there is the modulus of the complex number. This is Pythagoras theorem. So r, which is the modulus of the complex number z, would be equal to the square root of x squared plus y squared. So this line here is Pythagoras theorem. Pythagoras theorem. All right. Now, so that is how you determine the modulus. So the modulus is equal to the square root of the real part of the square root of the square of the real part of the complex number plus the square of the imaginary part of the complex number. Now, the argument of the complex number, which is this angle here, it's called the argument of the complex number z. So the argument of the complex number z is equal to tan inverse y over x. And that is simple trigonometry. Y is opposite to the angle theta. X is adjacent to the angle theta. The ratio that includes opposite and adjacent is tan. So the tangent of the angle theta is opposite y over adjacent x. So theta, which is the argument of the word complex number z, is equal to tan inverse y over x. Any problems so far?
Do you mind going over that one more time, please?
Which part?
Describing how we get by tan inverse.
This is the angle theta. Opposite to the angle theta is y. Adjacent to the angle theta is x. So the tangent of the angle theta is equal to opposite y over adjacent x. So theta now, the angle theta, remember if I know the tangent of an angle, to find the angle I must use tan inverse y over x. Please note, so the angle theta is called the argument of the complex number, and that angle is equal to tan inverse y over x.
Okay, sir.
All right, I'm going to erase that because I think I might need to write something in that space. Do I? I'm not so sure. All right, some notes on the modulus. Now, the modulus of a complex number is equal to the modulus of the conjugate of the complex number. That's what it is saying. And these are things that you can prove for yourself. The modulus of a complex number is equal to the modulus of the conjugate. So if you have a complex number z is equal to x plus iy, the modulus of z would be equal to the square root of x squared plus y squared. If you have the conjugate of that complex number is x minus iy, the modulus would be equal to the square root of x squared plus minus y squared. All right, and everybody should know that y squared and minus y squared is the same thing, because 3 squared is 9 and minus 3 squared is also 9. So these two things are equal. And they're also saying that the product of a complex number and its conjugate is equal to the square of the modulus of the complex number. Now, this is not groundbreaking information. It's something that you can easily prove for yourself. Argument. All right. Argument. So this says, argument is measured in radians. So this is notes about argument. First thing, argument is measured in radians. So what do you have to note? So if you deal with any form of calculation, complex number calculations that involve calculating the argument, you must set your calculator to radians. Now, argument is measured from the positive real axis. Argument is measured from the positive real axis. So the argument of a complex number is less than or equal to pi, but greater than or equal to minus, but greater than minus pi. This should be minus pi. I'm so sorry. So the argument must be less than or equal to positive pi, but greater than minus pi. And I'll give you and show you what we're talking about. So these are our quadrants, our 4 quadrants. This is the positive real axis, the real axis, and this is the imaginary axis. Now, argument is measured from the positive real axis. So it goes from 0 to positive pi. So this is positive pi, and it goes from 0 in the other direction to minus pi.
Sir, I didn't get that.
What part?
So because
positive pi and minus pi?
Yes, sir, because in my head I'm thinking on that side of the Cartesian plane is always negative.
Say it again?
In my head,
no,
I'm always
it is not dealing with coordinates, it's dealing with angles. So don't think of it in terms of coordinate, think about it in terms of angles. This is what, 90 degrees, sorry, 0. If you look at this as 0, this is 90 degrees, and this is 180 degrees. Remember now that pi radians is equal to 180 degrees. So it is not in terms of coordinate, it's in terms of angles. So going in this direction, it is from 0 to 180 degrees. Going in the other direction, it is from 0 to minus 180 degrees. So if you angles going from that positive real axis in an anti-clockwise direction, those angles are viewed as being positive. If you go in a clockwise direction, the angle is viewed as being negative. So that is when it is degrees, but when it's in radians, it's from 0 to positive pi and from 0 to negative pi. And 180 degrees is equal to pi radians. Any trouble? Any issues there, guys? Hello?
No, sir.
All right. Now, please note in the first quadrant, in the first and fourth quadrant, the argument of Z theta is equal to tan inverse pi over x. In the second quadrant, the argument theta is equal to pi plus tan inverse y over z over x. In the third quadrant, the argument is equal to minus pi tan inverse y over x. Now, you see, guys, that is not something so much to remember now as it is to understand. All right, so let us try and see why. What can you tell me about an angle in the channel? All right, let me come to a second.
Excuse me, sir.
Yes, go ahead.
Sir, so you have something else to write in those spaces?
Yes, I'm going to write something else in them now.
Okay, sir.
But Jamila, you didn't want me to erase
It's
them.
just that everything, no, everything you write, sir, they are of important value.
Remember, he's posting the
Here they are again.
video.
That's why I said it's okay. I can make note of it when the video is posted.
All right, guys, but let me just add. So let me try and draw some quadrants again. Everybody should know these are your quadrants: first, second, third, fourth. What can you tell me about sine, cosine, and tangent in the first quadrant?
They're all positive.
Very good. So you guys were taught properly. In the second quadrant, what can you tell me about sine, cosine, and tangent of an angle in the second quadrant?
Sine is positive and cosine and tan are negative.
Very good. In the third quadrant?
Cosine is positive and the rest are negative.
No.
No, tan is positive.
Tan is positive and the others are negative. And in the fourth quadrant?
Cos is positive and the others are.
All right. So look here now. It's the third quadrant where tan is negative. It means that the value of this is going to be less. It's all right. Don't worry about it. Let's get to it. But you need to remember, how do you determine argument for the different quadrants? In the first and fourth quadrant, the argument is just simply tan inverse y over x, where y is the imaginary part of the complex number and x is the real part. In the second quadrant, it is pi plus tan inverse y over x. In the third quadrant, it is minus pi plus tan inverse y over x. All right, 16. Example 16 says, find the modulus.
Sir?
Yes.
Sorry to continue. So the first and fourth quadrant have the same argument because that's where 0 is? Sir?
The first and fourth quadrant, no. It's just that in the first and fourth quadrant, all right, in the fourth quadrant, x is going to be, sorry, y is negative and x is positive. That's the fourth quadrant. In a sense, when you use a calculator, you're going to get a direct answer. You're going to get the answer. In the first and fourth quadrant, if you use a calculator, it will give you a straight answer. Now, in the second and third quadrant, if you use the calculator, it will not give you the correct answer. So if you're going to use a calculator now in the second and third quadrant, you have to put positive pi and negative pi before it, plus and then tan inverse, negative pi plus and then tan inverse in order to get the answer. And that is because whenever you, sorry, let me just say it. Whenever you Whenever you use tan inverse on your calculator, it is always going to give you an angle between 0 and 90 degrees. Please listen. Whenever you press tan inverse on your calculator, tan inverse or cos inverse or sine inverse, the calculator always return an angle that is between 0 and 90. If you want an angle that is between 90 and 180, you've got to do something else. You understand? So tan inverse in the first and fourth quadrant, where the angle is between 0 and what? And 90, tan inverse y over x will give you the direct answer. But if you want the answer in the second and what? Third quadrant, you're either going to have to put pi plus or minus pi plus before you put the tan inverse. Do you understand? Hello? Hello?
Yes, sir.
All right. Now, it's whenever you do this, if you cannot picture which quadrant the thing is in, you've got to draw a sketch. Sorry, this is just modulus. So if it's just modulus, here R, the mod of Z, would be equal to the square root of the real part, which is 2 squared, the square of the real part, plus the square of the imaginary part. So this is the square of what? 4 plus 1. This is the square root of 5. The modulus here would be the square root of 5. I'm going to stop the video.